So, again we will come back. So, therefore, we can write that I A 0 plus I B 0 plus I C 0 plus I N is equal to 0. This is equation 30, because neutral conductor is also there. It is shown here. You see, I have made a green circle with a dot, right, it is shown here. So, that means, but I A 0 is equal to I B 0 is equal to I C 0. Therefore, we get I N is equal to minus 3 I A 0. This is the equation 31. Now, we have studied that inductance thing, I mean much before. So, in that topic you go to, or in that chapter you go to equation 46. So, same equation 46 from the inductance chapter I am rewriting. So, that is a flux linkage of your conductor A due to that 0 sequence current, right. So, that means lambda A 0 is equal to 2 into 10 to the power minus 7 in bracket I A 0 ln 1 upon r dash plus I B 0 ln 1 upon d plus I C 0 ln 1 upon d plus I N ln 1 upon d n. This is equation 32. From equation 46 only, same equation we are applying here, right. So, lambda A 0 is equal to this one. Since I A 0 is equal to I B 0 is equal to I C 0 and I N is equal to minus 3 I A 0, here we have seen equation 31. So, what you do, you put all these things here, If you do so, just hold on, if you do so, you will get lambda A 0 is equal to 2 into 10 to the power minus 7 I A 0 ln d n cube r dash d square Weber transfer meter, because we have considered only 1 meter length of the transmission line. So, this is equation 33. Now, since L 0 is equal to the lambda A 0 upon I A 0, for inductance chapter several times we have seen this lambda by I several times. So, L 0 is equal to lambda A 0 upon I A 0, that is 0.2 ln the d n cube by r dash d square. This part can be written as L 0 is equal to 0.2 ln, then this part can be written d multiplied here multiply numerator and denominator by d. That means, you will get 0.2 ln d upon r dash into d n cube upon d cube. So, this d here it is d square, so it is d cube, but multiplied numerator denominator by d millihenry per kilometer. Now, this one you can write L 0 is equal to 0.2, that your 0.2 ln, this first part 0.2 ln d upon r dash plus 0.2 ln d n upon d whole cube, that is millihenry per your kilometer. I can put bracket here. So, that means, this is equal to, you can write that L 0 is equal to 0.2 ln upon d r dash plus this 3 into your 0.2 ln d n upon d. This is equation 34. That means, first term of equation 34 is positive sequence inductance, and this second term it is 0.2 ln d n by d n, it is defined as x n, right. That is the your you can define that the your ground this thing the ground reactance, or that the ground reactance, right, or neutral reactance, right. So, that way you can define it is 0.2 ln d n upon d. This is equation 34. So, that means, it is 3 times multiply. If this term is your x L 0 sorry x L n, then it will be 3 your x L n. So, anyway, so that means this one, that means we can make it as this is inductance, right. So, this can be converted to reactance multiplied by omega, this also can be multiplied by omega, right. That means, your x 0, that is the 0 sequence reactance, can be made as x 0 is equal to x 1 plus 3 x n. So, this x n your what you call this x n is equal to, this is your, this is actually L 0 sorry, this is actually your L 1 and this is L n. So, it is basically L 1 plus 3 L n. I am not writing here, but it is simple thing you will understand, and if you multiply by omega both side. So, it will be your omega L 1, that is your x 1, and it will be 3 your omega your this one is L n. So, it will be 3 x n. So, x 0 is equal to x 1 plus 3 x n, this is 35. That means, your for transmission line, that positive and negative sequence impedance they are same, say Z 1 is equal to Z 2. Here actually we can write also Z 0 is equal to Z 1 plus 3 Z n, same philosophy. So, there should not be any confusion, and for the 0 sequence we can see things are different. So, this is equation 35. Now, sequence impedance of synchronous impedances of synchronous machine. So, in this case, in the case of synchronous machine, that it is designed with symmetrical windings that you know, and you induce EMFs of positive sequence only. The positive sequence generated impedance is the value found when positive sequence current flows due to an imposed positive sequence set of voltages. This also known to you. So, neglecting the armature resistance, because R A is very small, so we can neglect it. The positive sequence impedance of the machine is, I mean, it depends on you. So, that means synchronous machine actually basically designed with symmetrical windings, and it induces EMF of positive sequence only. Therefore, the positive sequence generator impedance is the value found when positive sequence current flows due to an imposed positive sequence set of voltages. So, neglecting the armature resistance, the positive sequence impedance of the machine is, as per your requirement, the Z 1 can be written as J x d double dash if subtangent is of interest. This is equation 36. Z 1 is equal to J x d dash if tangent is of interest, equation 37, and Z 1 is equal to J x d if steady state value is of interest. This is equation 38. So, depending on your problem statement, accordingly whatever will be whatever will be asked, so accordingly you have to take these values. So, with the flow of negative sequence current in the stator, right, the net flux in the air gap rotates at the opposite direction to that of the rotor, because it is because of this negative sequence current, right. In the stator, the net flux in the air gap rotates at opposite direction to that of the rotor. That means, the net flux rotates twice the synchronous speed of the rotor. This is also known to you from your electrical machines. So, in this case, field winding actually has no influence, that field winding has no influence, because field voltage actually associated with the positive sequence variables, and only the damper winding produces an effect in the quadrature axis. So, therefore, the negative sequence impedance is very close to the positive sequence subtangent impedance. For example, Z 2 is approximately equal to J x d double dash. This is equation 39. That means, field winding also has no influence, and because field voltage is associated with the positive sequence variables, and only the damper winding produces an effect in the quadrature axis. So, therefore, the negative sequence impedance is very close to the positive sequence subtangent impedance, that is Z 2 is approximately equal to J x d double dash, that is for synchronous machine negative sequence impedance. And in a synchronous machine actually no zero sequence voltage is induced. So, zero sequence impedance of the machine is due to the flow of the zero sequence current. The flow of zero sequence current creates 3 mmfs which are in time phase, but are distributed in space phase by 120 degree. That means, the resultant is 0, right. So, I repeat this one, that in a synchronous machine actually no zero sequence voltage is induced, and zero sequence impedance of the machine is due to the flow of zero sequence current. The flow of zero sequence current creates 3 mmfs which are in time phase, but are distributed in space phase by 120 degree. That means, therefore, the resultant air gap flux would be 0, and there is no reactance due to armature reaction. Hence, machine only offers a very small reactance due to its leakage flux. Therefore, the rotor windings present leakage reactance only to the flow of zero sequence current, and that is Z 0 is equal to J X L, this equation 40. So, this is the zero sequence your what you call your impedance of the synchronous machine. It is nothing but that leakage reactance J X L, and your negative sequence will be approximately J x d double dash, approximately equal to subtangent reactance, and positive sequence of course, it depends on your requirement subtangent, transient or steady state. Now, this is actually positive sequence, negative sequence. Now, we have seen positive sequence, negative sequence and 0 sequence impedance for transformer and synchronous machine. Now, let us see this one. Now, sequence network of a loaded synchronous machine, because these are these are necessary. So, figure 3 I will come to that. So, a synchronous machine with neutral grounded through an impedance Zn. The machine is supplying your balanced 3-phase load. So, this is that your synchronous 3-phase synchronous machine supplying balanced 3-phase load. Balanced load is connected, but not shown, right. So, this is your synchronous ZS all our reactance is given for the machine, and it is your neutral, your what you call that neutral is grounded through that impedance Zn, that is taken, and this is the VA phase voltage VA, VB and VC, and current is IA, IB and IC, and these are the their magnitude is same, it is balanced actually EA, EB, EC, but they are separated by your what you call 180 degrees. Therefore, balanced 3-phase of synchronous machine is represented as a positive sequence set of phasors. That is EA we can same as before, only instead of V here it is E, EA is equal to EA, EB is equal to beta EA and EC is equal to beta square EA. Therefore, we can write like this: EA, EB, EC is equal to 1 beta beta square into EA. This is equation 41. Now, from figure 3, I mean from this equation, it is a from this equation you can write equation for EA, EB and VA, VB and VC. Each phase you can this equation you can write, apply KVL from this thing. So, you can write VA is equal to EA minus ZA IA minus Zn IN. That means, you apply KVL like this, the way I am showing here, it is make it plus VA, right, then your move like this, then Zn IN, right, minus your EA into ZS into IA, this way you write, then you will get VA is equal to EA minus after simplification, VA is equal to EA minus ZA minus Zn IN. Just let me show you this. Look, this is actually current flowing to this phase, it is IA ZS, right, then plus VA, then it is current, neutral current is flowing, plus Zn your IN, right, minus EA is equal to 0. That means, from this equation you can write that your VA IA ZS plus VA, from this equation you can write that VA is equal to EA minus your IA ZS minus Zn IN, right. So, similarly for phase B and C. So, that is why I am writing this VA is equal to EA minus your ZS IS minus Zn IN, then ZS IA minus VB is equal to similarly EB minus ZS IB minus Zn IN, and VC is equal to EC minus ZS IC minus Zn IN. That means, from this KVL, if you apply KVL, you will get this 3 equation. This is actually 42. Now, equation 42. Now, another thing is that this current IN is entering here, this way direction you have taken, this is leaving this thing, IA is leaving this terminal here, IA, here it is IB, IC, IN is equal to IA plus IB plus IC. That means, this also that neutral current IN, that is equal to IA plus IB plus IC. Now, using equation 42 and 43. So, this is equation your 42, right, and this is IN is equal to, given this IN you substitute here, this IN from here, IN is equal to IA plus IB plus IC, you substitute in equation 42. If you do so, you will get in this form that VA, VB, VC is equal to EA, EB, EC minus ZS plus Zn, then Zn, then Zn, ZS plus Zn, Zn plus ZS, it will be ZS plus Zn, and this is actually IA, IB, IC, this is equation 44. Or in compact form if you write, then Vp will be, this will define as a Vp, right, Vp will be equal to Ep minus this one will be Zp and this one will be Ip. This way you write in compact form, later we define. So, that means Ip is equal to this equation, actually this equation, right, to Ip is equal to, we write Ia, Ib, Ic transpose, Ep is equal to Ea, Eb, Ec transpose and Zp is equal to this matrix. And using equation 12, earlier I am not showing again equation 12, this we have, this we know now, Vp is equal to AVS. So, same way you can write Ep is equal to AES, right, same way we are writing. That means, and similarly we can write same way, we can write that your Ip is equal to AIS. This is that, this equation is 47, this is 47 and this equation is your 48. That means, Vs is equal to, you know, we have seen before Va1, Va2, Va0 transpose, Es is equal to A1, A2, A0 transpose and Is is equal to Ia1, Ia2, Ia0 transpose, and A matrix we also know, we have already defined, right. Therefore, you substitute, substituting expression of Vp, Ep and Ip from equation 46 and 46, 47 and 48 respectively into equation 45. That means, this equation whatever has been defined in this equation, you substitute everything from equation 46, 47 and 48. Then what you will get? You will get AVS is equal to AES minus Zp into A into Is. This is equation 49. And this equation 49 you multiply both sides by A inverse, multiply. Then you will get Vs is equal to Es minus A inverse Zp into A into Is. This is equation 50. Then Vs is equal to, we can write Es minus Zs dash Is, this is equation 51, where Zs dash is equal to A inverse Zp into A. So, Zs dash is equal to, this is your A inverse, already we have defined, and this is your Zp matrix and this is your A matrix. If you multiply all this, right, you will get Z dash is equal to Zs 0 0, 0 Zs 0 and 0 0 Zs plus 3 Zn. So, this is your Zs dash. That means, from this equation Vs actually, Vs is equal to Es minus this, Vs is equal to Es minus Z dash dash Is. So, Vs actually Va1, Va2, Va0, your Es actually A1, A2, A0 minus this is that your Z dash dash matrix, this is Z dash dash matrix into Is, Ia1, Ia2, Ia0, this is equation 53. So, from this note that A1 is equal to A, A2 is equal to A0 is equal to your what you call 0, because if you your what you call that that means Va1, Va2, Va0 that is your for synchronous machine, that in that positives only the positive sequence voltage is induced, right, that is A1 is equal to A, but there is no negative or 0 sequence voltages. That is why A2 is equal to A0 is equal to 0. That is why this equation can be written as Va1, Va2, Va0, this is Ea, A2 and A0 these two will be 0 minus this matrix, then Ia1, Ia2, Ia0, right. That means, that is Va1 will be Ea minus, from this equation only we are writing, from equation 54 only we are writing this, right. Therefore, Va1 is equal to Ea minus Z1 Ia1, that is equation 55, Va2 is equal to minus Z2 Ia2, that is equation 56 we are giving, and Va0 is equal to minus Z0 Ia0, this is equation 57, where Z1 is equal to Zs, Z2 is equal to Zs and Z0 is equal to Zs plus 3 Zn. That means, this is Z1 is equal to Zs, Z2 is equal to Zs and your Z0 is equal to Zs plus 3 Zn. So, that is why we are writing here Z1 is equal to Zs, this is actually Z1 is equal to Zs, Z2 Zs and Z0 is equal to Zs plus 3 Zn. So, positive, negative and zero sequence network of the synchronous machine is shown in figure 4. That means, for synchronous machine the positive, negative and zero sequence network, it is something like this, they are independent to each other. So, this is for your positive sequence network, this is voltage E A plus minus this Z1, current is given I A 1. So, negative sequence or negative sequence or zero sequence, they have no voltage source. So, it is Z2 I A 2 and it is Z0, current is I 0, this is V A 1, V A 2, V A 0. So, this is a positive sequence network, B is negative sequence network and C is zero sequence network for synchronous machine. Now, from the above your derivation, some observations we can make. First one is the 3 sequence networks are independent, these 3 networks are independent, no connectivity. The neutral of the system is the reference for positive and negative sequence network. That means, for positive this is reference. So, for positive and negative sequence network for synchronous machine, that neutral actually is the reference, whereas for your zero sequence network, ground is the reference. That means, that neutral of the system is the reference for positive and negative sequence network, but ground is the reference for the zero sequence network. Number 3, there is no voltage source in the negative or zero sequence network, only the positive sequence network has a voltage source. And number 4, the grounding impedance is reflected in the zero sequence network as 3 Zn. Although, when we are drawing the diagram it is Zn, but the grounding or what you call that grounding impedance actually is reflected in the zero sequence network as 3 Zn. So, now, see, this is for the synchronous machine, the positive, negative and zero sequence. Now, next is the sequence impedances of transformer. So, transformer actually is a static device. So, there is no rotating part in the transformer. So, the coal loss and the magnetizing current in the order of 1% of the rated value, and the hence magnetizing branch which is neglected. So, when we will find out the sequence impedances of the transformers, that magnetizing branch will be your neglected. So, the transformer actually is modeled with equivalent series leakage impedance. So, transformer is a static device, and if the phase sequence is changed, leakage impedance will not change, because it is a static device. Therefore, the positive, negative and zero sequence impedances are same and equal to leakage impedance of the transformer. That means, Z1 is equal to Z2 is equal to Z0 is equal to ZL. So, for transformer it is straightforward. Therefore, the equivalent circuit for the zero sequence impedance depends on the winding connection and also upon whether or not the neutrals are grounded, that means start delta, right. The zero sequence for the winding connection means start delta and also upon whether or not the neutrals are grounded. Based on that, the your what you call the zero sequence network comes. So, question is that this is 2 or there is 3-4 things for particularly the fault studies, the zero sequence diagram is quite important, because for positive sequence it will be in voltage source will be there and all the parameters as usual. For negative sequence there will be no voltage source, but all other parameters will be there. But for zero sequence that actually you have to understand that how one can draw, how one can analyze the things correct way, particularly the zero sequence diagram. This is from the aspect of student point of view, that their confusion actually mainly your zero sequence network. So, in this case for transformer case, for example, you consider star star transformer, both side it is grounded, it is both side is grounded, right, this star star connection. Look, as both neutrals are grounded and there is a path for the 0 sequence current to flow in the primary and secondary, because both are grounded. So, there will be a path for 0 sequence current to flow. So, figure 5a gives the equivalent 0 sequence circuit connection. Now, this is star star. So, this is A, B, C, this way I have drawn, this is also A dash, B dash, C dash I have drawn. The question is that your this is grounded, this is also grounded, both are grounded, right, this is also grounded, this is also grounded. That means that ground is the reference you take, and as both are grounded, so there is a path for 0 sequence current to flow. So, this is A and A dash, and this is your whatever this you saw that G for transformer, positive, negative and 0 sequence your impedance same as leakage or what you call leakage impedance, that is your ZL. So, this is A and A dash and this is a ground as a reference. So, this is the 0 sequence your network for the transformer for star star your connection, but both star are grounded. Now, next one is this thing you have to understand, otherwise difficult to solve fault problem and draw difficult for the 0 sequence network. So, next one is that star star again, but this primary side is grounded, but secondary side is your ungrounded, I mean no ground. So, this is the connection. So, in that case this is your star, right, this side is ground, primary side is grounded, this side is not. That means that primary neutral is grounded, but secondary neutral is not grounded, right, it is isolated, that secondary neutral is isolated. That means 0 sequence current in the secondary is 0, because it is there is no ground here. So, there is no question of your secondary side the 0 sequence current will flow. That means this diagram will be this, but this will remain open, because secondary side there is no 0 sequence current, no, it cannot flow. So, this is, but although this side is grounded, but this side is ungrounded. So, there is no secondary 0 sequence secondary current can flow. So, that is why this will remain open, but this reference line you have to show. I have this part, I have this thing understood. Thank you, again coming.